The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Great. Here we see that if we look here on our graph, we see here that isobaric is a straight line. So that straight line is demonstrating a constant pressure. So isobaric is telling us that the pressure is constant. Another way we can interpret this, according to our ideal gas law, is if our pressure is constant and our gas, then any increase in temperature is going to be an increase in volume, right? Say we have a piston here and then we have gas, and then we add a heat, and basically our temperature is increasing. What that's going to do is it's going to increase our volume. And that's why we see with isobaric processes the increase in volume. As we increase our temperature, right, we're seeing an increase in volume. That's what's being shown here. Okay, great. Now let's talk a little bit about the work here. As the volume expands, right, we said that the gas is doing work, so the volume expands. And if the gas is doing work, then what's happening is our work is going to be negative. Wonderful. Okay, now we can move ahead to our next slide. Let's talk about isochoric processes. If we look here, this is our isochoric process right here. Another word that you'll commonly see besides isochoric is isovolumetric. Isochoric, isovolumetric both just mean constant volume. And according to the ideal gas law, if the volume is constant and so is the gas, any increase in temperature will be an increase in pressure. If our piston here is fixed because it is constant volume, any increase in heat, we won't see any change in volume. What's actually happening is, as you go up our isochoric line here, we see that this will be an increase in temperature. Another way we can say this is going to be an increase in heat. Furthermore, earlier we said that work is the area under a graph. In isochoric processes, there is no work being done. As we see here, there's no area under the graph. So we know that work will equal 0. Now, if we remember our internal energy equation, it was anytime a system wants to exchange energy with its surroundings, it's always heat plus work. Since work is 0, the change in energy, in internal energy, is just the heat. So as we move up the isotherm here, we notice that the internal energy is also increasing as we go up. Perfect. Now let's move on to our next slide and do an example. What amount of work is needed to go from state A to state B and state B to state C? Okay, great. If we take a look here, we're talking about work, right? So doing our work equation, we see that work is equal to negative pressure times change in volume, and we're going from A to B. Let's just highlight that so we know what we're working with here. We're going from A to B. Okay, great. Here we don't have a change in pressure going from A to B, so our answer is just going to be here 5,000 pascals, right? And our change in volume, our final volume is going to be 30 meters cubed minus 10 meters, oh, acting a little funny, 10 meters cubed. Once we go ahead and we equate this, we should end up with a value of roughly 100,000 pascals meters cubed. If we recall, work is in joules. So how do we now get to work from here?